Hi, my name is Brian Caffo, and this is a lecture on regression to the mean in the Regression Coursera class. This is co-taught with my collaborators Jeff Leake and Roger Peng, and we're all in the Department of Biostatistics at the Johns Hopkins Bloomberg School of Public Health. So, regression to the mean is a historically very famous idea, and it basically answers the following question, or kind of answers the following question, let's say. Why is it children of very tall parents tend to be tall, but maybe not so tall as their parents? And why is it that children of very short parents tend to be short, but maybe not so short as their parents? And let's assume when we're discussing this, both parents are tall or both parents are short, just to avoid the discussion of or maybe the average height of the parents is tall and the average height of the parents is very short, and so on. Paradoxically, when we look at it the reverse way, the same is true. Why do parents of very short children tend to be short, but not quite as short as their child? And the same thing is parents of very tall children tend to be very tall, but maybe not quite as tall as their children. And you know, this idea tends to pop up quite a bit. Why do the best performing athletes this year tend to do a little worse the following year? Almost always. And that's a famous idea, and it's called regression to the mean. So anyway, it was invented by Francis Galton in his paper, Regression Toward Mediocrity in Hereditary Stature. Here's, I give the exact citation, it was in 1886. So here's the way to think about this. Imagine if you just simulated random Gaussian variables. Then the largest one, the largest first ones would just be the largest by chance. And the probability that it's smaller for the second simulation is quite high, right? So, you know, let's say I simulate a lot of normals and I take one that's 3, right? 3 is pretty large for a standard normal. Then if I were to simulate another one that was going to be its paired measurement, the chance that it's lower than 3 is quite high. In fact, it's 99% that it's going to be lower. Or in other words, the probability y is less than x given x gets bigger as x heads towards very large values. Similarly, the probability y greater than x is given x equals x gets bigger as x heads to very small values. So you might say when you're talking about, let's say, sport athletes, when we're talking about performance in a sport, there's maybe two components. There is this randomness, this element that's not under their control, and then there's this part that maybe the very best athletes are better because they're intrinsically better, or they trained harder or whatever, but they happen to be better at whatever sport it is they're playing. So there's this intrinsic part, and let's just think of maybe for the purposes right now that the regression line is the intrinsic part. And if that correlation isn't perfect, then there's that leftover random part, and the random part is the component that derives the regression to the mean. So you can think in terms of an athlete, their performance in a given year is part their ability. Some baseball players are just better at batting than other baseball players. But if they're a little bit lucky as well and have a great year, then the chance that they're going to be a little bit worse the next year is high.